Hello everybody. In this video, we're going to learn about an application of matrix algebra called migration models. So imagine this scenario. There's some kind of a population. This could be a population of birds or a population of fish or any other animal that travels between locations. Let's say this population is divided between two regions, not necessarily equally divided, but part of that population lives in a place I'll call area alpha, and the other part of the population lives in a place called area beta. Let's also assume that known percentages migrate between these two regions, or these two areas, at regular intervals. It could be every month or it could be every year. The interval depends on the population. Again, you could imagine this as maybe fish swimming between two ponds which are connected by rivers. Maybe you have some birds which are flying from north to south and back again. This could be used for many different applications. So, what we'd like to do is two major goals. First, if we know what the population is at the start, the population in each area, determine how the population is distributed at a given time. And by distributed, I mean how much of the population is now in area alpha and how much of the population is then in area beta. And so that information, we'll keep track of that using a vector. And finally, we'd like to figure out what's the long-term population distribution, right? Does the population oscillate between these two areas? Does it kind of even out? Maybe eventually everything will end up in one area. And like here, for instance, you've constantly got 30% of the population of area B, or area beta, going into area alpha. Does it all end up here? What happens? Well, math will tell us the answer to that. And it does stabilize, and we'll figure out to what values in each area. All right, so let's look at that particular example. And here, this is a less colorful version of the diagram. We've got area alpha and area beta. Let's assume, I'll say t is maybe measured in years. So I have some unit for t. Let's say each year, 10% of the population moves from alpha to beta. And at the same time, each year, 30% of the population of beta moves to alpha. Right, so these percentages refer to the original area here. In addition, we can derive two more numbers which will be important. If 10% of the population of area alpha moves to area beta, that means 90% of the population stays in area alpha. Similarly, if 30% of the population leaves area beta, that means 70% of the population stays in area beta. And I'm indicating the population that stays by this arrow which goes from each region and points back to itself. Should also say, for a simplifying assumption here, we're assuming that the population stays constant, right? That there are no births or deaths in either population, right? So those are our assumptions. These are the numbers. And for our notation, let's think of p of t as a function which tells us the two populations at time t. And so p of t is like a vector output function, right? At any time t is a single number, the output will be a vector where the first component gives us the population in area alpha, and the second component gives us the population in area beta. So we need some kind of initial populations to kind of do some math. So let's assume, I'm just making this up, that the total population is 140, and at time 0, area alpha contains 60 and area beta contains 80. Now, how can we calculate the populations in each area at time 1? Well, let's see, for this first population, for area alpha, what's the new population of area alpha going to be? Well, it's going to keep 90% of that original 60, right, that stay in that population. Also, we're going to add in 30% of the population from beta, which was initially 80. Right, these are the arrows that point into area alpha. And so they both contribute. In this case, that would be 54 plus 24, which is 78. So the population here during time 1 becomes 78. So that population went way up. To calculate the population in area beta, right, we know that 10% from area alpha migrates over to area beta. And so 10%, or 0.10, times that original 60 from alpha, plus 70% of the population that was originally in area beta stays there. And so 70% of 80, so that's 0.70 times 80. And we do the math, and the new population is 62. And so this will be the population distribution at time 1. We do exactly the same calculation to figure out the population at time 2. Except now, the population at time 2 depends on the population at time 1. So these numbers inside these second sets of parentheses refer to the populations of alpha and beta at time 1. So for instance, the population of area alpha at time 2 is going to be 90% of the population at time 1, plus 30% coming over from beta, so 30% of the population from beta at time 1. And then when we add those up, these are the values we get. And if these populations, if this is like a number of creatures of some sort, we should consider this as an approximation. This doesn't mean to say that 8/10 of a creature migrated from one area to another. That doesn't make sense. So we'll think of this as an approximation, which we could round to get an answer if we wanted to know the population in time 2. And so the pattern here, right? Well, let me go back here, right? Notice this pattern, something times something plus something times something. That looks like a dot product style calculation. Whenever you see something like this, that means matrix multiplication is lurking in the background. So the general pattern is this. To calculate this year's population, again assuming t is measured in years, right, p of t would be equal to this matrix times the vector p of t minus 1, which you can think of as last year's population. Right, so this year's population can be calculated by using these percentages and multiplying them by last year's population in the style of a matrix vector product. Equivalently, if you want, you can think about this as you can calculate next year's population in terms of this year's population. Again, multiplying by the same matrix. And these two equations are really equivalent. Right? In each case, they're saying to figure out the value at a certain year, you're going to multiply this matrix times the previous year. This matrix here, with these different percentages, this is called a migration matrix, or sometimes it's called a transition matrix. And to create this matrix in general, right, the rows tell you how much is going to be migrating to a particular location. Right, this first row, these numbers A and B, those refer to percentages going into area alpha. And here, the second row, right, those are the percentages coming into area beta. The columns, you can think of it as the percentages leaving from each one of these areas. Right, so these numbers A and C, the 90 and the 10, those were the percentages leaving area alpha. And the second column, 30 and 70, those were the percentages leaving area beta. And because everyone has to be accounted for, those percentages leaving an area, right, those should always add up to 1. And by leaving an area, I'm including, the population's travels from beta to beta. So each one of these columns, the numbers should sum to 1. And I'm thinking of them as percentages, so these will generally be decimal values between 0 and 1. Right, so in general, we'll have this formula. The population at time t is equal to the migration matrix M times the population at time t minus 1. So how would you calculate, for example, the population at time 3? Well, the population at time 3, that's M times the population at time 2. But then this begs the question, how do you calculate the population at time 2? Well, the population at time 2, that's the matrix times the population at time 1. Well, how do you calculate the population at time 1? Well, that's the matrix times the population at time 0. And that's the piece of information you're typically given. Time starts at 0. And so, if you gather these m's together, notice there's 3 of them. Right? The population at time 3, you can think of that as m cubed times the population at time 0. And this pattern holds for really any number, not just 3. In general, to calculate the population at time t, you could also think of that as the matrix to the tth power times p of 0. Sometimes p of 0 is called the initial population vector, right? The number of creatures living in each one of those areas. And so, if we're talking about powers of a matrix, as we discussed in an earlier video, diagonalization is really helpful to calculate powers of a matrix. But diagonalization, in turn, depends on eigenvalues and eigenvectors. And that's going to help us simplify our calculation, especially if we want to know the population far into the future. That will require us to know a large power of this matrix, and diagonalization makes that calculation a lot easier. So in this case, in every case when we calculate diagonalization, we'll set up the eigenvalue, eigenvector calculations, the determinant of m minus lambda times the identity matrix. And as always, we subtract lambda from these values. And in this case, when I'm writing these, I'm always worried I'm going to miss that decimal point. So I always like to put a 0 in front of the decimal point and to make sure it doesn't get lost. And also, I really don't need these zeros over here, right? So 0.90 is really the same thing as 0.9. That's why I wrote it differently down here. So calculate the determinant of this matrix the same way we normally do, working with decimal values, so we just have to pay attention to where the decimal point goes. But after we expand this and then group like terms, you'll find that you have lambda squared minus 1.6 lambda plus 0.6 equals 0. And even though there's decimals in this quadratic equation, it still factors nicely. In fact, as we'll see between this example and the next example, factoring characteristic polynomials corresponding to matrix or corresponding to a migration matrix is actually even easier. In this case, this polynomial factors into lambda minus 1 and lambda minus 0.6, which tells us the eigenvalues are 1 and 0.6. Once we have eigenvalues, we then proceed to calculate eigenvectors, and the same process as before. Right? And even though we do have decimal values, right, even after we do the subtraction, right, we still notice that these equations there is some redundancy in these equations, right? One equation should be a multiple of the other equation. We can still pick, and we still should pick, nice whole numbers for our free variables. Right here in particular, if you pick 3 for v1, you can pick 1 for v2. So you get a nice eigenvector there. The eigenvector for eigenvalue lambda equals 1. That eigenvector is 3, 1. Similar calculation, I won't read out the entire thing. If you want, you can pause the video and write it down or read through it. But at the end, with the eigenvalue kappa equals 0.6, you can find that the eigenvector is 1, -1. Once you have the eigenvalues and eigenvectors, you're ready to move on and complete the diagonalization. Recall that the diagonalization of a matrix means writing it as in the form P times D times P inverse. D is the diagonal matrix, where the entries along the diagonal are the eigenvalues. P is the eigenvector matrix, meaning the columns of P are the eigenvectors we just calculated. So for this current example, the diagonal matrix D is 1, 0, 0, and 0.6. The eigenvector matrix P is 3, 1, 1, -1. You can calculate the inverse of this matrix. The determinant in this case is -3 minus 1, so that's -4. So each of these entries will be multiplied by -1/4. And here's our inverse matrix, 1/4, 1/4, 1/4, -3/4. And, as always, if we want to raise to a large power, or really to raise to any power, right, for the diagonalization, m to the power n is equal to p times d to the n times p inverse. And d to the n is easy to calculate. So this formula for the population at time t, and here we've got two things called p, right, traditionally, so I'm trying to write the function as kind of a cursive lowercase p to distinguish that. P of t, which is equal to the matrix m to the tth power times the initial population vector p of 0, that's equal to matrix p times matrix d to the tth power times matrix p to the -1 times the initial population p of 0. Now, one thing we're often interested in is what's going to happen in the long term after many months or many years pass. Right? Does the population stabilize? Does it fluctuate? What happens? In other words, what happens for large values of t? What happens as t gets large? And so it's really convenient to borrow some notation from calculus. We're not actually doing calculus, but I do like to use this notation. Right? As t gets large, that's something from calculus called the limit as t approaches infinity. Right? We can't necessarily plug in infinity, right? Because what does it mean to multiply something by itself infinitely many times? But we can say as t gets very large, what happens to the size of each of these values? Right? No matter how large t gets, when you keep multiplying 1 by itself, that's 1. And meanwhile, this number, 0.6 to the tth power, if there's a number between 0 and 1 that you're raising to a high power, right, so some small fraction less than 1, that number actually gets smaller and smaller as you raise it to a higher and higher power. So this entry in the matrix approaches 0. And so as t gets large, this matrix gets closer to this matrix. That's going to help us analyze the long-term population distribution. Right? So if we take the limit of this function, in other words, let t get large, that really just affects the diagonal matrix. We replace the diagonal matrix with this matrix right here. That's actually great. I love multiplying by this matrix because of the single 1 and all the zeros. Works out pretty nice. So let's multiply P, the first matrix, times this matrix. We'll get 3, 0, 1, 0. Then we'll multiply this by P inverse, pulling down P inverse onto the second line. Right? We get a bunch of fractions here, 3/4, 3/4, 1/4, 1/4. And finally, let's do the matrix vector product. Let's multiply it by that initial population vector. We'll get 3/4 times 60 plus 3/4 times 80. That's 105. A nice whole number. That worked out nicely. And similarly, a fourth times 60 plus a fourth times 80, that's 35. And just as a check, we assume that none of the members of our population are dying. There are no new members being born or introduced in any way. This population is still a constant. It's still 140. So it reaches an equilibrium, right? The population of area alpha keeps getting closer and closer to 105. The population of area beta keeps getting closer and closer to 35. Right? We got that from some matrix algebra. Now, here's something really interesting. Right? There's some patterns you might notice here. For example, we have the same number on the top and on the top row and the bottom row once you multiply p times d times p inverse. Right? And what this leads us to is the following interesting fact. The initial population is actually totally irrelevant to this kind of a problem. Right? The initial population does make a difference in the year-to-year population, but no matter what the initial distribution is, it's always going to tend towards this same answer. Right? So, for example, let's assume that the total population is still 140. And let's look at the most general case. Right? Let's say the population at time 0 in area alpha, let's just call that n. So the remainder of the population, which will be in area beta, well, that's going to be 140 minus n. Right, so if you calculate this matrix product, this is p times d to the t times p inverse. If you multiply that by this initial population, right, notice that we're going to have, for instance, across the top, 3/4 times n plus 3/4 times the quantity 140 minus n. When you expand that out, right, the 3/4 n and the 3/4 minus n cancel, leaving you with 3/4 of 140, the original population. And the second part of this matrix, and again, this n and this negative n are getting multiplied by the same thing. They cancel out, leaving us with 1/4 times 140. So, right, no matter what n was, that doesn't figure into the final answer. Right, so it's a strong equilibrium. Right, the way I like to think about this as, imagine you had some kind of a bowl, and then you put a marble anywhere inside that bowl. Right, eventually, no matter where it starts off, it's going to end up rolling around and going through different values or different points, but it ends up at the bottom of the bowl. Same idea here with an equilibrium. Right? The initial population makes a difference for the intermediate values, but at the end, this is where it's going to tend to. We should do one more example. I'm always a fan of doing multiple examples so we can kind of see the patterns in the calculations. All the examples will be two areas. Let's assume in this case, area alpha and area beta, at each time interval, 50% migrates from area alpha to area beta. Meanwhile, 40% migrates from area beta to area alpha. We can therefore deduce that 60% stays within area beta and 50% stays within area alpha. Let's also assume that the initial populations are 200 in area alpha and 300 in area beta. So we'd like to set up the matrix model and figure out what this matrix is, figure out an equation, and then figure out the long-term distribution. So as before, the matrix model contains these transition or these migration percentages arranged in this form. So to alpha from alpha, that's the 0.5. To alpha from beta, that's that 0.4. To beta from alpha, that's this 0.5. And to beta from beta, That's that 0.6. And as always, we can check. We can see that these columns sum to 1. So it's looking good. The equation we can write as, just like before, this will always be the case for migration models, P of t is equal to the matrix M times P of t minus 1, which means, for the same reasons we discussed before, P of t can be written as the matrix M to the power t times the initial population P of 0, or if we diagonalize this, P times d to the t times P inverse times the initial population vector P0. So we need to calculate the eigenvalues and eigenvectors of this matrix. Right, subtract lambda from the diagonal entries, calculate the determinant, expand, group like terms, and factor. And once again, this factors, in this case, it factors into lambda minus 1 and lambda minus 0.1. Right? In this case, that means the eigenvalues are 1 and 0.1. And in general, we'll always get 1 as one of our eigenvalues when we do migration models, and the other eigenvalue must be less than 1. Right? You can never have an eigenvalue greater than 1, because that would make your matrix larger and larger as t goes to infinity. Right? So these eigenvalues always have to be 1 or something less than 1. They can't both be less than 1, because in that case, the power of the diagonal matrix would become all zeros, and it would be as if your population was dying out. But we're assuming a constant population. That's why one of these will always be 1, and the other will be a positive number less than 1. So as before, we'll calculate eigenvectors corresponding to these eigenvalues. For lambda equals 1, I subtract 1 from the diagonal entries, convert to a system, and pick some numbers which help this work out nicely. So here 4 and 5. Then for our other eigenvalue, subtract that from the diagonal entries, convert the matrix equation into a system, and pick some values for your eigenvector. Nice integers make it easier. All right, once you have the eigenvectors, we now put them together to get our diagonalization. Right, here's our diagonal matrix with the eigenvalues. Here's the eigenvector matrix, whose columns are eigenvectors. And then the inverse of that matrix, here the determinant is -9. To calculate the long-term distribution, again we need to calculate this product, and just like before, d to the tth power, right, is the matrix 1, 0, 0, 0 as t goes towards infinity. Because 1 to any power is 1, and a small number to a large power approaches 0. When you multiply this out, you're going to notice the same pattern again. In this case, right, we get the constant 4/9 across the first row and 5/9 across the second row. When you calculate the matrix vector product, you get approximately this. Right? So the area alpha population should get closer and closer to 222, while the area beta population should get closer and closer to 278. And so this is how we analyze population models or migration models using matrix algebra. In theory, you could do this for more than 2 populations. You could do it for 3 or more. Then you'd also need to diagonalize a 3x3 or an n×n matrix. And we're not going to do that here. But this hopefully gives you the general idea. As you know, I like to say, you learn math by doing math. So in this case, I won't have you start a new problem from scratch. Let's kind of validate that this answer makes sense. The initial population, oh, my lights just went out. Oh, that's better. So in these problems, right, the starting populations were 200 for area alpha and 300 for area beta. if you multiply those values times this migration matrix, right, you can use that to calculate the actual population at time 1 and the actual population at time 2. So go ahead and do those calculations, figure out what those populations are going to be, and in theory, they should be getting closer to this value. All right, so that's all we're going to have to say about migration models. Thanks for watching.